And I have enjoyed so much my correspondence with Carl Littmann. He keeps sending me these big stacks of stuff with all his wonderful drawings that he spent so much time making. And he's just discovered some amazing things about just volume ratios. If you take 3 circles and put them together and try to get another circle inside, and to say what's the ratio of the radius of that to some other thing, it turns out, or let's say 3 or 4 spheres, and you put a sphere inside that tetrahedron, you get these ratios that end up being the ratio of the muon to the electron, or the 1836. You keep getting all these numbers. It's like, I don't know why, but he keeps getting them. So he's been working on this for years, and I don't want to take any more of his time. Carl, come on up and show us all your magic numbers.
Well, thank you very much. Just give me a second.
Okay, well, we don't need slides immediately. My talk is on 3 topics, but I think they're all related to the ether. The pion particle, Lord Kelvin's ether density and its relevance today, and the overly broad conclusions of Einstein's special theory of relativity. We'll be starting with the first slide. Thank you. Shortly, and while things are coming up, I thought I'd pass around a few things that are somewhat relevant. Not everybody need get one immediately because there are some on the back table. Well, anyway, somewhat like this, shown on the slide, some of the sketches there, some are new and some are old, but they all show how some neat patterns consist of large and small spheres, and how those large and small volumes correspond proportionally to the large and small particles masses occurring in real nature, such as the proton and electron. The average pion particle, versus the electron particle is shown. Well, it has the mass ratio of 270 to 1. And near the top of my slide, there I show how that particle mass ratio corresponds very closely with the sphere volume ratio in that old upper pattern, that 270.1 to 1. And other particle mass ratios match other pattern volume ratios too, almost exactly, as you may see when time allows from the papers passed around, which you can keep, but there are some on the back table also. Now, I have recently discovered another mass pattern, another sphere pattern, as shown in the slide's lower sketch. And that also generates the same volume ratio, 270.1 to 1. The more roads to a truth or to a particle ratio, the stronger its manifestations in nature, it seems. In that bottom sketch, the small electron spheres lie entirely inside the interior of the bigger spheres as we generate up to our pion size. And as shown, we can build up to even larger structures by using substructures based on similar triangle patterns. And that is called fractal structuring and is a hierarchical means of building up. In previous papers, I used the largest sphere shown and averaged it together with a kaon sphere not shown there to construct my proton-to-electron mass ratio estimate. I think that real ethereal space exists, and that it has structures somewhat like the ones shown, and that helps determine particle characteristics. So let's talk next about ether density, its history, and its implications. Next slide, please. In 1854, Lord Kelvin calculated his minimum density estimate for ether near the Earth. In today's commonly used units, his ether density comes out 10 to the minus 19 kilograms per cubic meter. His creative estimate was nicely noted by Maxwell and Tate, among others. From my own various methods of estimating, I think that Lord Kelvin's estimate for ether density near the Earth is also a fairly good estimate of ether anywhere in our universe, which is remarkable because I think that Lord Kelvin made some wrong presumptions, but some of his errors were nearly canceled out by his others, and some good fortune limited the fallout from his main misconception. More on that later. Incidentally, the ratio of his rarefied ether density to that of thick nuclear matter equates to roughly the strength of a gravitational weak forces to the strong nuclear forces in our universe. Density is a term in Bernoulli's fluid flow equation, so low and high flow densities can cause low and high suctions respectively, and that may relate to fundamental forces in our universe. The velocity of fluids can also be a factor, of course. Let us look at some ether concepts in Lord Kelvin's day to roughly appreciate his approach. Let us try to imagine that our very hot sun over a period of 1 second creates and emits a thin ethereal slug of light or some undulations 186,000 miles long, and that slug widens somewhat as it flies or undulates through space toward the Earth, and it hits a 1 square foot collection pan on Earth, and there its heat is deposited and measured. By knowing the heat delivered in 1 second and the speed of the 186,000 mile long ether beam, its width and thus its volume, we can further deduce this. Unless that long ether slug had a minimum mass density, its volume could not have contained enough mass to deliver enough kinetic energy to heat our pan as fast as measured. So we can calculate a minimum ether density required. Next slide, please. Okay. Here's why I think Lord Kelvin was lucky that his estimate even got close. High energy photons can be made in 2 very different ways. There, that way, and we'll concentrate first on the one in the lower sketch. There, the bodies do not use any ether from their nearby surroundings to make the photons. They are just made, roughly speaking, by the body simply splitting off large chunks from their own selves and heaving it away as photons. A simple self-cannibalizing case of equals mc squared. Like in fusion and in fission bonds and in electron-positron annihilations. And this below here shows the annihilations and what flies away. That is what Einstein predicted. And great and commendable for Einstein's equals mc squared paper so far, as Einstein wrote, a photon with energy E is radiated away from the scene, and the emitter's mass is diminished by E divided by c squared. Thus, very near those types of emitting bodies, the emission mass density is almost as high as nuclear matter itself, for a brief time at least. So Lord Kelvin's method would have utterly failed there, since no ether was used there to make photons in the first place. Ether is irrelevant there. But now contrast that to a photon made when the Bohr hydrogen atom undergoes electron jumping from a distant outer orbit to an inner orbit. And emits a photon away from the scene. In that case, an Einstein special relativity paper is utterly wrong by stating this: when a photon of energy E is emitted, the mass of the emitting body decreases by that photon's energy divided by c squared. But note, in the Bohr atom's case, its now closely orbiting electron gained that much extra mass in kinetic energy, not lost it. And it gained a mass because the hydrogen atom and its electrons scooped mass out of the ether enough to do both the following: to create and send the photon away with its energy and mass, and to also add to the presumed emitter, the hydrogen atom, more mass and kinetic energy for its own atomic self. It gained mass, not lost it. A glaring error in Einstein's paper, frankly, when we try to apply it to atomic hydrogen. And I remind you, if more mass is added to a mass already moving, and its velocity is not decreased, then its inertia is increased. About 6 years after the Bohr paper, Einstein kindly wrote Lorentz and in effect apologized for earlier stating, by earlier denying ether's material-like aspects. Einstein was then trying to explain his recent general relativity theory. And by 1930, Einstein likely realized that kinetic energy and mass are lost to ethereal space when ballistics exceed planets and stars escape velocity requirements. So he then remarked that his previous superfluous ether or space seemed to be getting its revenge by eating up matter. Although I don't have time to speculate on all the details, fortunately our sun's surface makes many of its emitted photons by scooping mass for them out of the ether, instead of only by directly cannibalizing its own mass and sending that to us directly. So lucky Lord Kelvin made fairly good estimates after all, instead of a disaster. In fact, I wish Lord Kelvin would have used a more typical story than our sun, one not quite hot enough to melt tungsten, or even better, used a hot tungsten strip filament near its melting point and near his measuring instruments. Tungsten is a metal with the highest melting point and tensile strength, and I think it maintains a tensile strength as long as a real ether density flows through it and is not interrupted, converted, or subverted for something else, like the continuous production of photon flow of a density comparable to that of ethers. That remains admittedly as speculation, but I attempt to give a few more details in the NPA Proceedings book. Einstein's inertia and special relativity errors are evident when studying the Bohr hydrogen atom. But that offers us an opportunity for suggesting improvements in general relativity and better appreciating its themes. That is, by applying aspects of Bohr's theory to gravity in stars and orbiting planets, not just orbiting electrons. Consider when two distant equal cold stars gravitationally come together and or intersect or interacts so as to closely orbit each other. Yes, Larmor, Einstein, and I would naturally expect timers on them to slow down, but many other questions naturally arise, including if the bodies collided and when and then cool down, and thus if the bodies of the now merged bodies are equal again to the original separated ones. Would the actual measurable mc squared energy that the merged masses could deliver to the universe now be less than when the bodies were separated, say if an internal nuclear bomb blasted them apart? That is because of their now higher escape velocity requirement, that added gravitational impediment. So for those merged bodies, should a negative gravitational correction term be inserted to modify its new impaired mc squared capability? And suppose a timer is midway between two mutually orbiting stars where there is no net pull more in one direction than another direction, and thus no falling elevator analogy. The timers, is the timer still there in the middle, slowed down? Its mc squared energy deliverable to the four-way universe is still slightly reduced. Many treatments of general relativity ignore those simple questions or just throws a lot of tensors at us, seemingly to obfuscate addressing such questions. Now, a few words about another Einstein paper inferring that there is no establishable correct claim as to which body is closer to absolute rest when one body seems to pass the other at super high speed. Some NPA members have previously addressed this topic, but perhaps in more abstract terms than my now simple, more down-to-earth attempt. Time is short, so I'll try to be shorter than the paper. Yes, most stuff in the universe, such as solar wind, receding or approaching or orbiting stars or galaxies, and interstellar or intergalactic dust do move at very high velocities. But all of that is still very slow. I repeat, very slow compared to the speed of light. And I think ether indirectly helps keep that so. So we can reasonably and roughly estimate an average velocity for all the stuff near us as being nearly zero velocity or very slow compared to the much faster speed of light. And by using that very expensive telescopes and thus focusing on nearby stars and galaxies, we can gather further evidence supporting that. So I want to point out at least two thought experiments, maybe even real possible experiments, to help establish what is near absolute rest. Take two hollow straws, each with a sticky interior and with a diaphragm going through it, separating their north chamber from their south chamber. With equal rocket fuel, launch one straw, say at 1/100th the speed of light toward a few degrees away from the North Star, and one southward. No collisions with the stars, please. Let each straw have a similarly built-in timer aboard, and let each record the amount of cosmic dust accumulated in its north chamber versus the south chamber over a period of time. Note that even a northbound traveling wind drifting at 1/1000th the speed of light would still be easily scooped up by the much faster northbound straw's north chamber, but not its south chamber. And in a similarly very short time, according to its slowed up onboard timer. So asymmetries are noted when we travel super fast. That's my main theme in this part. Asymmetries are noted when we travel super fast. Somewhat similarly, an even faster traveling northbound rocket, say at 2/10 the speed of light, would notice a Doppler blue shift, spectral blue shift, looking at stars northward, and a red shift of stars if its instruments look southward. Yes, there are some receding and approaching stars and galaxies relative to us on Earth, but no easily seen ones have such high speeds as to drown out the Doppler shift that would be seen by our super high-speed rocket and its instruments. So we can tell the super fast from the comparatively slow. So I think that on the cosmic level, we can better understand some major behaviors of the universe by considering that the universe abhors some aspects of Einstein relativity. That being said, I still do respect several of Einstein's relativity contributions and his often overlooked other scientific work too. Thank you, and now if there's any time for questions or comments.
We have 10 minutes.
Okay.
It's okay. Are there any questions? Come on forward if you have them. If not, we're behind anyway, so it'd be great to catch up. All right. Thank you.
Okay, well, thank you.